welcome to part B of this series. So again, the task was to model these and try to reproduce the results in MATLAB Simulink. So the model that we intend to achieve at the end of the operation. So we have several components that we need to model here. The reference position, the X3, you have the servo controller, you have the command that we feed to the mechanism. So these we intend to model these one pretty much. So for the output to give it to their feedback, as well as used in the adaptive law and the filter operation as well. So after that we get this, and this one we model it after getting through those parameters, and we feed it to the servo controller also. In the first series we did model this equation, basically the first part, but you see again, if you go down a little bit, which is also this one. So in the second part there's the combined 4 and 5 to have a much simpler equation 6, which has everything. So as you can see, this one remains, now the TD, the TL, the TF. Now the TF was integrated using these equations, as you can see them here, up to this point 5, 6, up to here, thereabout. So I modeled this one as well and found the same results. So this one, as you can see right here, it represents this entire equation that is modeled. As you can see, you have the two integrators, the x1 and the x2. Then we get x1 the input to x1 and all that. So just quick, we have as you start here, k1, g1, phi1, we multiply by u. Also use the input we are getting from the outside, that is the control signal input. We multiply the two, then that one is a plus, the remaining are just subtraction. Subtraction. The next one, we implement this phi2, which is the same k2 over j2, just like k2 over j. J is the inertia, multiply, you get theta 2, we multiply by x2 again. From there we continue phi 3. How do we get phi 3? We use this calculation. So we use gamma 1 times j, times 1 over j, and that. Alternatively, we just have a constant here, you put it over one of the same. How can we implement this? Instead of writing 1 over j, I can also use it as let's write j, and I'll do the reciprocal using the math function. Okay, yeah, you can just search for math functions. So it continues on and on. So here, so this theta 3, which can be found using this one. This is the theta 3. First of all, we get the theta 3, and we put it aside. Then math reciprocal. You can use any other functions that you want, attributes, exponential, logs, and all that. So we have the reciprocal here. You can just pass it to get put here j, pass it through the signal. So one and the same thing. Many ways of killing a rat. So we continue. So this one, as you can see here, beta 1 times x2. So look here, find beta 1 here. Beta 1 times x2. We pass it through a tan h functions right here, as you can see. Then this one we subtract the beta 2 times x2 again, pass it through. Then the answer between the two multiply by theta 3. So all those is implemented quite well. Again, theta 4, we can see it here, gamma 2 over j. So you get gamma 2, then multiply by j, we get theta 4. Then we multiply by beta 3 times x2. So come here, you find beta 3, right? some x2, multiply it, you get the tan h part of it. Then of course multiply by theta 4, you feed it to the negative side, as you can see here. And of course with the theta 5, of course theta 5 is gamma 3 over j, the same thing. So gamma 3 times j, you get theta 5. We multiply it by using the x2 again, and the answer we get it, we feed it there. So pretty much straightforward equation. So from here I have a couple of outputs from the signal. Of course, after all that we add the delta. So delta, I get it outside theta 6, I also get it outside theta 6 is TL, and we have given TL outside again. Then delta denotes the disturbances, small disturbances, so you can either put a 0 or can either leave it or include. So I decided to include it. So again, some scopes to visualize x1 and x2 internal scopes. So the output I'm outputting, what I need x1 output, I need this beta 1, beta 2, and also beta 3, because I'm using the externals. So data 1, this is the input. Output are those ones as shown for you, beta 1, beta 2, beta 3, as well as x1 and x2. Okay, just x1, I don't need x2, external one, because I need it later. Of course k2, and of course the control input u. So from here, the next part was the adaptive control with design guaranteed parameter expression. Now, so after here, the whole system is complete. Let me just enlarge it. So the whole system is done. You can maybe rerun this simulation, which will of course produce the same results as the other one. So this pretty much everything is so the gamma, these are just some constants which I defined in the MATLAB workspace. You can just create it, you can edit it, expression and all that. Open, you can change the value the way you want it. So that's pretty much for the, and then I build a Collier subsystem for equation 16. There's one subsystem for equation 6, not 16. So it's for equation 6. Point of correction now. I have some TL, some delta, and some manual switch there. Input and all that. I get x1, those beta. This one is a control signal again. I'll come back to it. Initially we had put it at a constant value of, let's say, 1 volt, so we need to vary it to follow this the desired position. So the next part of the equation, we focus on equation 16. This is the one that we focus on. Why? Because we let z1 be the difference between x1 and d. x1 is the position, x is the desired position, and then first order sliding surface and the associated error r. So this is the associated error r, and this one also we are going to need it. So we get x2 z2 equals to z1, not all that. So how do we model this? So we have 3 equations that we need to model. This one is the first one, second and third one. You can just take this one and put it right here, so that you can z1 equals to this. And if you come to equation 17, 18, 19 and 19, it's just about more the same, expanding this by implementing this adaptive equation 16. How do you know that? One is pretty much simple. Let me just show. We take this one, of course we take the two signals. Already we have x1 from the previous equation here. We can get x1 from here. We multiply, we subtract xd. What is xd? Is the desired position tracking, and in this first round, if you come here, xd will be given as a sinusoidal with sinusoidal function with 0.1 as the amplitude, with 2 pi as the frequency. Now, of course, all these are in radians. So let's go and model that. We have everything, and some of the parameters that maybe we need are also given. K2, Z2 for the controller and all that. You can get them from here as well as that. So you have K1, K2, and KS, L, and all that. So then here we have those parameters. You can go beta 1, beta 2, and all that, gamma 1, and everything, gamma 2, gamma 3, K1, all the parameters are here. So let me open up the Simulink design for the controller, which is right here. Okay, so this one we are going step by step. So equation 16, so let me just open it. So you get the 2, get that one, get the difference, you multiply by Z1. So Z1 not, this means that we need to differentiate. That's going to need to be differentiated. So the Z1 we differentiate, get Z0, and then you multiply by, we add the 2 Z0, and then of course this one K1 plus Z1 initially. From here we get Z2, the signal as you can see here, Z2, that when you're done, and then we come R. How do we get R? We take that as Z2 naught, so you take this signal, we differentiate it to get Z2 dot, Z2 dot, and then you take that and differentiate signal multiplied by K2, you get Z2, and that is K2 Z2. From there we add the 2, we get our R. Now this R isn't going to be used, and we can just visualize it, or you can put a terminator on it if you want, so it's not going to be connected per se anywhere. I'm right clicking by doing this, so just move it as well. So that's pretty much it. Now the next part is modeling equation 20. This is all about equation 16. We only need this one. This is a Simulink. This one is just an explanation, the mathematics behind it, the theory, but this one is the one we model. So you don't need to model these ones. So we need to just model the equation 16 only. From here you come to the controller design equation 20. So you model equation 20 and model equation 21. So that will be in our next part C episode. So see you until then.